Hello, everyone. Thank you so much for coming to this session on Rubin 2036. I know it's the end of the week and we're all tired, but I really appreciate it. As a reminder, I know you've seen these reminders the whole week, but I think they're important and actually I really like them and I try to use them in the meetings that I organize. And very important that we have a code of conduct and harassment is not tolerated and unprofessional conduct. So we do have point of contacts and we adhere to the principles of kindness, trust, respect, and diversity of viewpoints and inclusiveness. So this is important. Keep it in mind for your future meetings as well to do something like this. Also, for people who are on Zoom, please keep muted and you'll have the opportunity to speak. And for people who are here in the room, please wait a little bit if you want to talk and we'll pass you the microphone. For this session, like in other sessions, we do have a channel in the Slack space for this meeting. There's already been some interesting discussion and points there, and I have actually shared some of the material that we'll be sharing in the workshop next week. So this session was defined. So we want, as you know, we want to do this workshop called Rubin 2036 here at KaiPAC next week. And this session was designed for those of you who cannot attend in person or who want to start a little bit early, but we would like to gather your inputs today. And then, well, as you know, the Rubin Observatory, the LSST was ranked in the previous decadal survey. It was the top ground-based priority. Not the previous one, the 2 decadal surveys ago, but yeah, but actually now, right now, we are in the mid-decadal, like the National Academies of Sciences is assembling the panel to assess see how we're doing with the most recent decadal survey. So we're doing this workshop in order to ask us the question about what we should do with the Rubin Observatory after the LSST and to think about the type of science cases and white papers that we want to write for this decadal survey. So there have been previous efforts that I have documented here related to previous workshops related on similar topics, also for other white papers for Astro 2020 and SNOMAS papers. I'm not gonna talk a lot about this. Aaron might say some words about this, but we wanna acknowledge these efforts and build on that. So the workshop, we have the goal of the workshop that over 3 days, we want to write a document or a roadmap that will hopefully inform the type of white papers that we want to write for the next decadal survey. But we also want to focus on the science cases that will help us inform that decision. And also, of course, we don't do science in the vacuum, and there's always constraints regarding to funding and everything. But we want this workshop also to focus on the science cases while keeping those constraints in mind. And our interest is to build these compelling and community-driven science cases that will lead that process. So one of the questions that I asked the participants or the people who were going to register for this workshop is, what do you think is the single most compelling opportunity for post-LSST Rubin? And at the end of this session, hopefully we'll have some time to have a discussion about that. And then you can give me your answer to that question. And I was actually impressed and happy that there were a lot of people interested in participating in the workshop. So we're gonna have about 60 people in person and another 50 online and with different career stages of so the way we decided to organize this workshop based on the input that we got from the scientific organizing committee and the input that we got from the participants that registered to the workshop. We organized this meeting in 5 different groups or themes. And these are the themes that also that I'm gonna ask you to think about later at the end of the session. So one of them is continue the LSST style survey, for example, or do we have alternative cadences or footprints? A lot of you are interested in doing narrow or medium band surveys or with different filters, for example, or having different targets of opportunity or with doing multi-messenger astronomy, or do we have a different instrument, a different type of focal plane? And hopefully, probably, maybe you have an idea that at first doesn't fit here. Maybe you can try to fit it here, or otherwise we'll just make another category and that's fine. This is just a guideline. And then what we're gonna have the participants of the workshop in order to have a more structured discussion is to gather in groups among these 5 topics and then answer some prompts, some sort of questions in order to help us write this document that we want to write in the end. So we're going to ask participants to write the specific science goal they have in mind, why the Rubin Observatory, and why in this moment. One of our members of the SOC was saying, like, here we're kind of preaching to the choir, like, what about the people the skeptics, like, what would be the skeptics' objection to your case, and what would be your answer? What type of needs will you have from Rubin, like, in terms of different changes or and the time scales? Another question that we want to ask people is the prior. Some people were saying, oh, maybe it's too early because we don't have the science results from the LSST. I would like to wait 2 or 3 years for the LSST to, inform my decision. So if you had like a crystal ball, and what kind of science result would you need from the early LSST results in order to inform your science case? We also think about success metrics or figures of metrics, and then as well about connections with other facilities or synergies. Then at the end, what would be the next steps after this workshop? Maybe we do another workshop, but in the end, we also want to, as I said, write this document that will tell us the type, this roadmap that will tell us the type of documents we want to write for the decadal. And then there are two extra factors that accompany these 8 questions in terms of the role of AI in your science question, AI, machine learning, agentic AI, generative AI, and also Chilean engagement, or Latin American engagement, in particular Chilean engagement and co-leadership, because this is an opportunity to think about like what things that we should have done when we started Rubin or the LSST that maybe now we can do, right? And this is one of the points that came up in the discussions with the SOC. Again, this is an example of the thing. So this is another opportunity of thinking about other stuff that you would like to think if you had a time machine, what would you have told the people back in the time. So, well, after these introductory slides, we're going to have a few talks from some of the contributors. And then after that, hopefully we can have an open discussion. I want to hear from you. But also you can maybe work in small groups. Maybe this is not the best setup, but I wanted to mirror what the structure of the workshop will be next week, which is a workshop and when I have a lot of discussion. So please, you can use these slides to take notes, or if you feel more comfortable with yet another Google document, that's fine. The important thing is that that we write down your thoughts, and I will make sure to incorporate that feedback in the product that we will have next week. So you can use the questions that I have asked and the prompts above, and then you can keep your notes here. So yeah, thank you. So after this, we're gonna do our introductions. I'm sorry, after the talks after this introduction, I think Aaron Rootman is now gonna tell us his thoughts about this. So oh, thank you. Okay.
No questions for you?
Yeah, do you have any questions? I mean, it's very informal and it's Friday, so. But it's okay. Let's go with the talks, and then we'll have the discussion. I'm gonna have time for discussion.
Let's see, how do I move forward?
With the big button, you move forward, and the little one.
So I mean, Andres gave a good introduction to what we're going to do next week, what the goals are. I'll just make a few editorial comments on top of that. One or two people asked me, why are we holding this workshop now? We just started the LSST a couple of weeks ago. Why are we worried about 2036? Okay. There are maybe 3 reasons. Andres kind of alluded to them. One, we actually don't have a plan past the 10-year LSST. And technically, it's actually not funded. So we've gotten a pretty strong commitment. I'm looking at Ed here for the next 10 years. But past that is really open. So we have to do something about that. Second, if any of what we want to do requires significant resources between now and then, we have to propose and prepare for it. That doesn't go quickly. Third, as I think in this crowd everyone knows, there are different prioritization processes that happen community-wide. The decadal survey presumably will happen something like in 2030, and that is not actually that far away. For those of it who are DOE funded, sort of the DOE side of this project, there's a parallel process that doesn't go in a strict decadal time frame, but there will be another one of those prioritization processes sometime soon, certainly before 2036. So as a community, we have to be ready for that. And of course, that doesn't happen, instantaneously. And so this workshop is really designed to be an opening salvo towards those goals of having some very solid, strongly motivated, compelling proposals for the 2036, so the post-LSST era for Rubin Observatory. Okay. In the run-up to the last set of prioritization, there was plenty of work. There were actually a set of workshops even before that period. There were a couple workshops in the run-up to the decadal survey. There were a whole suite of white papers. So those are, that's work that we'll take advantage of going forward. And maybe. Okay. So I'm going to make an editorial comment about all that previous work. It really focused mostly on the instrument side. What could we do to modify and improve Rubin Observatory? And I would say much less on what you would do with any of those possible changes. And so I think that drove a lot of the thinking for next week's workshop to focus much more on the scientific exploitation of the future, which might have one of three kind of directions. And those directions came out of these previous studies. And those were the things that were on Andres's slide. Narrow band or medium band filters, different cadence of observation, and target of opportunities, and maybe continued observing in the same way as LSST. So that is a highly editorial comment that those are the items that look most plausible for the future, and that we wanted this workshop to focus mostly on those. And that's really an outgrowth of all of the work that was done 5+ years ago. So this repeats what Andres said. I think that finishes my editorial comments. And I think we've got a number of talks more focused on what you could do in this future period. So we should go to those.
Thank you. Any questions? Yeah, Sean. Yeah, can you come? Thank you. Wait, what is this? Oh, okay, thank you. Yeah, I switched the order a little bit.
This on? All right, wonderful. All right, thank you very much for giving me a few minutes to speak about one potential avenue for using and maximizing Rubin Observatory in the future. I'd like to lay out the themes that Andres started with. And while each of these are very interesting in their own right, it's quite likely that Rubin Observatory will encompass each of them to some different weight or balance. I'm going to focus on part D today. And one specific subcomponent of part D, a large portion of my time nowadays is focused on target of opportunity observations with the LSST, but the landscape in 2036 is quite likely going to be very, very different than the landscape that we have now. So I work a lot on gravitational wave cosmology and gravitational wave astrophysics physics, linking gravitational wave observations to electromagnetic observations that we make with Rubin. I'll show here the map of the current gravitational wave observatories. Two things to note here is one, we will be having a new interferometer available starting in 2030 with LIGO India. And sadly, at the end of this year, GEO 600 will be turning off. So these are some of the changes that will happen over the duration of the LSST that will inform the LSST period. Now, there's plenty of things on the horizon in the 2036 and 2040s. And so I've highlighted the three main new facilities. Two are on the ground. On the left here, you have Cosmic Explorer led by the NSF. This is a 40-kilometer version of the LIGO detectors. And then similarly, the Einstein telescope, which is led out of Europe. There are two design configurations under discussion. The one that's shown here is the triangle configuration. And there is also LISA, which is led by ESA, but is also sponsored significantly by NASA. So these are the three facilities that people are thinking about in the 2035 plus regime. Those time scales, okay, so this is relevant. The question was, are those timescales realistic? All of these timescales are independent of budget delays, falling pianos, anything that may derail any of these large multinational projects. So this is the best estimate that we can give. And even though it is pretty reasonable to expect that 2035 may become 2037 or 2040, this still lines up quite well with the end of the LSST. So with these new facilities comes a new scale. So what you're seeing here is actually the observable universe that we will be able to probe with these gravitational wave observatories, both with binary neutron stars in yellow and binary black holes on the right. And so one thing you'll notice is that we're now going to much, much deeper redshifts that we're able to detect with the gravitational wave observatories, which means that Rubin, if enabled and empowered to do so, could play a very strong role in identifying the electromagnetic counterparts to some of these events. And so I'll start today with the gravitational wave landscape. So I talked a little bit about LIGO, Virgo, and Cagra. They all have a sensitivity curve that is what you would tend to see over here on the right. And the way to read these sensitivity curves is that you're sensitive to everything above this floor. So this curve acts as a floor, and anything above it, the detectors can detect. Now this is today. Obviously you have pulsar timing arrays that are looking at the stochastic background. And this is what 2036 will look like. And one thing you'll notice is that we have this mid-frequency band here that is accessible by LISA. And if you flip back and forth, you'll see that advanced LIGO, the bucket moves very much lower, which means we can detect fainter and further away objects. So those are the two main differences between the gravitational wave landscape today and in 10 years from now. So I've highlighted four of the main science drivers that I believe gravitational wave astrophysics and cosmology can benefit from with using Rubin Observatory. This actually spans not just cosmology, which is my main focus, but also host astrophysics, departures from general relativity, and also improvements in the understanding of the host astrophysics that seed these gravitational wave events. Many of these four science drivers, I believe, are very cross-cutting. So while it may primarily benefit astrophysics, some of them may benefit in cosmology or other fields. To answer the question if Rubin is good for these kinds of searches, I'd posit that the Rubin field of view is actually ideal for many of these searches. So since we have larger detectors with hopefully better technology, we'll be able to localize many of these events much, much better. You can see the average localization probability or localization area on the x-axis here. And what you'll see is that where Euclid or Roman, which is the next dashed line here, can observe in one single pointing, everything to the left, there's this large gap between Euclid and Rubin in terms of the kinds of events that you can localize in a single pointing. And so I would argue that the existing Rubin focal plane and the existing Rubin field of view is very well suited for directly imaging the regions of interest around these gravitational wave events. Yeah, sure. I missed it.
That this is assuming that the Einstein telescope and the Cosmic Explorer are observing simultaneously.
Yes, that's correct. So yeah, so the question was, can you say something about the axes? So what you're seeing on the x-axis is the localization area on the sky. Typically in gravitational wave cosmology and astronomy, we term the localization area by what fraction or what percentage of the 90% localization area you can see. That's basically how we say this is the relevant area on the sky we want to tile with Rubin or other telescopes. And then on the y-axis, this is just shown with the fractional luminosity distance contribution here. So lower on this plane is higher signal to noise gravitational wave mergers, things that are better localized in volume space. Yeah, in the yeah. Yeah, and so colored by signal to noise. So the darker objects down here, these are your loudest gravitational wave signals, and the least loud that you can still detect are up here in the top right of this plot. So you probably would ask now, okay, can Rubin even detect any of these things? So with LISA, there's one primary electromagnetic counterpart that we're looking for. It's mergers from massive binary black hole systems. And through some studies that have been focused primarily on Einstein telescope, we can actually show that we are able to detect these counterparts out to a redshift of 4. A lot of this has to do with the AGN disk and the density of the disk and which model you're using. Currently, to date, there have been no confirmed electromagnetic counterparts to AGN disk emission associated with massive black hole binary mergers. But it's still, even if you assume a more less optimistic disk model, the horizon of detection with Rubin drops from redshift of 4 to redshift of 2, where you can still probe a lot of interesting astrophysics and cosmology. So to answer, can you detect it with any LISA counterparts with Rubin? Yes, you can. Similarly, moving from the massive black hole binary to the stellar mass or hundreds of stellar mass, hundreds of solar mass black hole binary and binary neutron star events, Rubin can detect 100 that are localized well by Einstein telescope in a year. And this is some of the work by Nandini, who's going to talk in just a few minutes. But what I'd like to emphasize is that by going deeper, we are able to detect these binary neutron stars. And we're very quickly transitioning from the regime that we're in now, where we do not have an overwhelming wealth of gravitational wave data, to the regime 10 years from now, where we will be starved looking around for telescope time in order to accurately image many of these counterparts. So that's all I have right now. More than happy to help lead the discussion afterwards. Thank you.
So Sean, that last number, that 100, is that extrapolating from the 1? Or yeah, what goes into that number?
That's a really good question. So what goes into that number? If you go back to slide, sorry. If you go to slide 3 here, what you'll see is our current horizon distance is right around this A+ line, this blue line. And for the binary neutron stars, you can see it actually, really, we can only go out to about redshift 0.15, 0.2. By going with Cosmic Explorer and Einstein telescope, we're moving out to a much, much larger area. So we're just getting much more volume, sensitive volume, by having a much larger detector, 40 kilometers versus 3. So.
Okay, this is exciting, but I'll be the, I'll ask the questions that they said somebody who's skeptical might ask. So after that 1, I remember when we were talking about it, we were going to see like 1 a month, right? Yeah. So I'm sure if you would have made that plot after the 1, that yellow band would have been in closer, right? So why do you think it's realistic? And then the follow-up question is, I actually believe we're going to see neutron star mergers because we know there's some counterpart there. But for black hole mergers, isn't it the case that we might not see them at all?
To answer the second question, yes. It is highly dependent on the disk, the accretion disk around the black hole mergers, either on the multiple solar mass scale or on the supermassive scale. To answer your first question, the band itself would not be moved in. It would actually be thicker. So what we're doing every single time we have another observing run is we go and we look for neutron stars. We do not find any, and we revise the rates lower and lower and lower. Certainly, the next time we'll have two, that band may be updated to be a little bit thicker. Okay, sorry.
Okay, thank you, Sean.
I'll start introducing myself. So good afternoon. Thank you for being here this late in the day on the Friday after a very intense and wonderful RCW. I'm Nandini Hazra. I'm a postdoc at the NCBJ in Warsaw. And for this talk, I will assume that Sean has convinced you why we need to have all this time dedicated to TO in 2036 and forward. And so I will talk about how we can go and harvest more of these kilonova events using Rubin in the era of the Einstein telescope. So that's a very big monitor. I'm going to. Okay, so just to recap what Sean said, this is the map of the first generation of Earth-based gravitational wave detectors that we have now. In this list, you can see the ones that are operational and will be operational for hopefully the next decade with certain upgrades, namely LIGO Hanford, LIGO Livingston in the US, Virgo in Italy, and then Kagra in Japan. They have detected the wonderful gravitational wave multi-messenger event, GW170817, which had these very interesting fast decaying blue component, and then this more slowly evolving red component, which was deemed a kilonova and was associated with the nucleosynthesis of heavy elements. Followed by this, there was this other binary neutron star merger event, GW190425, but in spite of extensive follow-up efforts, which included several people in this room, including Shreya, who's there, no no electromagnetic counterpart, no kilonova counterpart to this event was observed. So in spite of all our best efforts, even though we would like it to be different, multi-messenger astronomy with gravitational waves has been not a routine astronomy that we do, that we see events once a month. And this is not something that is very common. And in fact, no BNS mergers were observed in the 04 run with very high confidence. So we are very much expecting and hoping that there are more of these events. So these are rare events currently with our understanding. And in the second generation of the gravitational wave instruments, we will have these upgrades to LIGO and Virgo. And there will be the addition, as Sean said, of LIGO India. And this will bring us to O5 sensitivity in the early 2030s. But what is then the third generation of gravitational wave instruments? So on the Earth, we will have the Einstein telescope and Cosmic Explorer. And there have been different configurations proposed for the Einstein telescope. I'll get into that in a minute. And for this presentation, I will conveniently ignore all the things that are off Earth. So for example, LISA in space, or interesting things like the lunar gravitational wave antenna, which will be maybe on the moon. The Einstein telescope was envisioned as this triangular underground detector with these xylophone nested interferometers with a high frequency and low frequency component. And it was part of the S3 roadmap. And this is how it was envisioned. And the idea was to have this improved sensitivity at low frequencies so that the binary neutron star merger would spend longer in this sensitive band and therefore be localized better using the imprint of the Earth's rotation. And the projection is that we will, with the Einstein telescope, observe an order of 100 events, BNS events, localized better than 100 square degrees, and an order of 10 localized even better than 10 square degrees, which is agreeably within the purview of Rubin's field of view and localization capabilities. Currently, the target of opportunity strategy for Rubin has been already proposed by a team of people inside the Transcendent Variable Science Collaboration, and this is being revised after the TO workshop at Berkeley a couple of months ago. And if you notice in this figure, the maximum exposures that we go to using these follow-up strategies is up to 180 seconds. What I will suggest to you is outrageous, but bear with me. If we increase the exposure of our target of opportunity observations to 600 seconds and more, we can reach deeper sensitivities, we can go fainter, and therefore discover more distant kilonova transients and get more multi-messenger events in this way. And I will convince you, I will try to convince you that we can do this with investing very little of Rubin's annual time. We can capitalize in this way on the increased localization capabilities of the Einstein telescope, but not only the Einstein telescope working alone, but in networks with other detectors that will be hopefully operational then. Different, as Sean mentioned, different configurations of the ET were studied. In particular, the triangle and the 2L configurations were considered. Different alignments of the 2Ls were considered, different arm lengths were considered. So this has been in the works for a very long time. As of January, a declaration of intent has been signed between the region of Sardinia in Italy and the region of Saxony in Germany. And the site selection is supposed to happen this year and is well on track. As I mentioned, we will observe an order of 100 well-localized BNS events, localized better than 100 square degrees. And this is for all the of the Einstein telescope. So whichever configuration we get, we will still do very, very well in this large numbers of very well-localized BNS mergers that we will have. To try and understand how this impacts our multi-messenger capabilities, we did an end-to-end study as part of the Einstein telescope collaboration, focusing on Rubin's capacities in localizing these multi-messenger events by tiling the area of localization that these events would give us. We started with an astrophysical population of BNS mergers, and then we associated them to a gravitational wave signal and an electromagnetic signal, and then considered what we get at the end of it. That's a lot of technical details. Let's get to the meaty parts. We considered exposures of 600 seconds and 1,800 seconds. We considered only a 2-filter strategy, which was more economical, which allowed us to go deeper, go fainter, and get more events out of this effort. We adopted a mosaic strategy, which is standard within the TO community currently. And we considered very lax 5 sigma threshold detection strategies, detection criteria for the kilonovae themselves. We found that investing a few percentage of Rubin time, we could get up to 100 kilonovae per year using these strategies. The 600-second strategy was a little more economical. The 1,800-second strategy gave us an improvement, but it was prohibitively expensive for the amount of benefit that it gave us. What we found at the end of this study was that we would get between 30 and 100 kilonovae per year in all the configurations that were proposed for ET. Additionally, we found that the low frequency component of ET, which is cryogenically cooled, is crucial to this effort. And the better localization that it provides to the BNS event is what really gives us this big edge in getting and harvesting more kilonova counterparts. So what I want to say here is that as early as 2024, Rubin's capabilities in 2036 and beyond is already something that has been shaping the gravitational wave science and the decisions that go into making these infrastructure choices. We made another detailed study. So we refined the simulations that we had. We considered different BNS merger rates, optimistic and pessimistic. We considered the configurations of ET, both the triangle and the 2L, in networks with LVKI, so the second generation still being operational in the 2030s, and networks with Cosmic Explorer. We did this host of 64 simulations that you can see here. And to each, we attached a more realistic target of opportunity strategy. We're considering the real footprint of Rubin, so on and so forth, by considering the extinction and adding all of this into the simulation to make it more and more realistic. To fraction of these events, we also added GRB afterglows to consider the common impact of the kilonova and GRB event in the electromagnetic bands. We found with this simulation that even with the pessimistic kilonova, with the pessimistic BNS merger rate, and taking up around 2% of Rubin's time, we can get up to hundreds of kilonovae detections in 10 years. So divide everything by 10. If we look at the projections for the optimistic rate, this increases significantly and gets us up to 100 kilonovae per year. So the reality is that probably we would have something between 10 and 100 kilonovae per year using these strategies. And look again at the percentage of Rubin time, which is in the brackets, which is around 10%, even with the very optimistic BNS merger rate. So we are well within budget and we're getting very high returns. We like that. In particular, what we want to impress upon you is that it is also very important to keep the second generation gravitational wave observatories operational, because this gives us an even higher boost and gives us an order of magnitude improvement in kilonova detections, going from ET working alone to ET in a network with LVKI. ET in a network with Cosmic Explorer does not seem to give such a high increase, as you can see from this figure as well. And this, we think, is because Rubin reaches a natural threshold beyond which it cannot go very, very far in redshift. This is an efficiency curve of what we see in our detections, and there is a natural fall off around redshift 0.3 for kilonovae especially. The GRB, which are the fainter histograms, go up to a little bit higher redshifts, and this is natural because these are all coming from lower inclination events. Making a comparison with the second generation detectors, we think that the LVKI cannot outperform ET alone, but LVKI in a network with Einstein telescope can give us such a boost in localization that we can get many, many kilonovae events detected per year. And if we perform slightly longer exposures for these very, very well localized events with ET and LVKI, which are localized better than 20 square degrees, so it's very easy for Rubin to tile them. And if we use 1,200 second exposures, it allows us to reach even higher distances. That's the end of my pitch. I hope you're convinced. I will end my talk with the pictures of the people who have been involved in this work: Eleonora Lofredo, Uliana Duplezza, Marika Branchesi, and myself. That's the QR code of our paper if you're interested. And I will leave you with this figure, which allows you to choose your degree of threshold of all the BNS merger events that you want to follow. And if you make a straight line up and then a horizontal line there, it tells you what percentage of Rubin time you need to use, what number of hours in 10 years you need to use with Rubin in order to get all of those events followed up. Thank you.
So LSST cannot take exposures longer than about 30 seconds because of the sky brightness. So I assume that you're talking about co-added imaging, but it would have to be co-added imaging over a fairly big field in order to discover these things. No, I'm talking about dynamic range of the experiment. We can't. The sky is so bright that we can't really expose for 600 seconds. We can't do that. So it would have to be. It would have to be some kind of. Yeah. Yeah. So, yeah. I mean, we could do it in the U band.
Yes. So this is a very first preliminary simulation, set of simulations that we've done. I think the way forward is to go with coads, increments of, and this is something that needs to be figured out in the next 10 years. There's something that needs to be
And that would
at.
also help avoid the satellite issue, which is
That's right.
pretty bad.
That's right.
Hello, Nandini.
Hi, Pat.
So if you were on the optimistic side of your rates, how many things will we detect in LSST proper in the next 10 years? And would that change sort of like our scientific interest in the list of things you listed?
So,
so say that you're on the optimistic side. So in this scenario, like where you got like hundreds, but we're already, the event rate is what it is. So then that means that we're also going to detect more things in the 10 years of LSST survey. Is anything, yeah, does anything become sort of, we get so many in the 10 years of LSST that they become obsolete even for this plan and you don't care anymore because we know them?
That is true, but I think with the 30-second cadence that we have, and without co-adding all of these exposures at the same time during follow-up, I think the distance that we can push for these counterparts with the targeted follow-up is still larger. So I think with the standard cadence that we have currently, and even with the TO cadence that we
In the TO, we do go deeper, right?
we do good, we do
yeah.
good, but we still go only up to 120, 180 seconds. The argument I'm making, and correct me if I'm wrong, is I think if we do this increase, this very, very high increase, and then follow up a lot of events, we will still go to higher, see more kilonewton farther away, and then we can also see if they look different in different.
Sure. And my argument was not meant to like push back on any of these, but just like, so long as we're optimistic, like,
Yeah,
I
I
want to know
think-
what we're gonna kill with LSST in the 10 years.
And I think a very interesting case would also be to see what kilonewton we see serendipitously, and that is Igor's work. And I think that is interesting in and of itself. What if we can do more?
So as you envision this, the role of LSST is just to find these things, as it were. Once you've found it, then you bring every telescope to
Yes.
bear to
Yes.
study in great detail. And then there's an interesting scientific question about, what are all the interesting things you need to learn, and how many neutron star mergers do you need for that? But that's probably a whole other topic.
So that
Yeah.
is something that the Einstein telescope collaboration itself is also considered. And it seems that if we stay between these optimistic and pessimistic rates, I think on a few years of observations, we can start to make sub-percent constraints on the Hubble constant. And then all of these host galaxy studies that we can do, and all of the science that comes with it. So
I just have one comment on what Fed is saying that I think is very, very timely to say, oh, if the TO program does good, there's probably some scientific questions we don't need to answer. But the one thing that Nandini alluded to, and is on one of her previous slides, is that the accessible volume that is also detectable by Rubin is larger and deeper than what the current gravitational wave detectors can sense. So you're going from, an upper limit of about 0.4, 0.5 that is both jointly detectable by Rubin plus the gravitational wave detectors. With the next generation of detectors, you're talking about a redshift of anywhere from 2 to 4. And you can do a lot of very interesting studies in those redshifts. So
that plot is also somewhere in the slides. If you scroll down. Yeah, if you keep scrolling, the slides are up on the website. So if you keep scrolling down, that plot is also there. Thank you.
Thank Nandini again. Thank you. We have a couple of more talks.
So today I want to introduce a new survey by HSC called the HSC NIJI. So here NIJI means, well, it's written in it doesn't work. Okay, but anyway, so this is a kanji and this is a hiragana. Well, in Japanese, this means a rainbow. So I'm from Hironao Miyatake from Nagoya University of Japan, and leading this survey. Well, I understand that in the next week we are going to focus on the science, but as for preparation, let me just introduce this survey. I will make some small comments on the science cases, but mainly today I'm going to talk about the survey itself. Okay, how can I go ahead? Big water. Okay, so I think many of you are familiar with Subaru HSC, but let me introduce what is HSC in this slide. So right, so well, Subaru is an 8-meter telescope, and it has a prime focus. So HSC is a 1.5 diameter field of view, and then so it's put in prime focus. So right, and then HSC has a really good seeing, routinely 0.6 arc second. And so, well, with HSC, so we have done HSC Subaru Strategic Program Survey. So that had started in 2014 and then was completed in at the end of 2021. So HSC has a wide layer. So it's written in wine red in this map. And then, so it has about 1,000 square degrees covered by GRIZY, and the limiting magnitude is 26. And then, well, this wide layer was designed for wavelength and cosmology. Well, one thing I'd like to note is that final cosmology results from the HSC, we have been, we are still working on it, and then we hope get out those results in early next year. So, well, taking advantage of this survey, so we started a new, well, we started the new survey HSC NIJI, as I said. So with the HSC NIJI, so we use the newly fabricated medium bands. So it's shown from blue to red here, covering 400 nanometers to the 10,000 nanometers by 16 bands. And we got all the funding to fabricate those 16 band filters. So first 12, first 12 filters. So it's funded by the Japanese government, JSPS Kakenhi. PI is Satoshi Miyazaki, who was actually a PI of the HSC SSP. And the remaining 4 filters on the radar end, well, actually it was funded by NSF. So H. Egami in University of Arizona, Stewart Observatory. So well, he got that grant to fabricate 4 filters. And so, well, the unique point of this medium band is 4 filters are put into a single frame, as shown in a photo on the right. And then it's called a quadrant. So we call the first 4 blue filters are put into a single frame, and then we call this frame medium band quadrant 1 or MBQ1. And then consecutively next bluer bands, 4 bands, that filters are called MBQ2, and then MBQ3 and MBQ4. So why we went for this design? That is because for Subaru, for HSC, it takes 30 minutes for the filter exchange. So we don't want to lose 30 minutes every time we change the filters. Rather than that, we just rotate the camera to cover all the sky. And then, so the rotation itself takes like less than 1 minute, given that the readout by HSC is like 30 seconds. Well, it's not really, well, it doesn't slow down the survey. Well, the MBQ1 was delivered in summer 2025, and that photo is actually MBQ1. So then with this MBQ1, we started HSC NIJI. So where HSC NIJI is, well, that photo is a workshop we had last month. So, well, HSC NIJI consists of the Japanese community, of course, but there are lots of interests from the other communities like University of Hawaii and Gemini and Keck community. So they all have access to the several times, and then they agreed to coordinate our proposals to get more nights. And so and then this survey, where I myself is a cosmologist, and so where my main motivation is of course cosmology, but after doing several workshops so far, it's a community workshop held in Japan, we found a lot of science cases already, including protoclusters, galaxies, AGN, and going to smaller scales like galactic archaeology, and also a solar system. And so we plan to conduct wide and deep surveys. So wide will cover about 1,000 square degrees, overlapping with HSC SSP wide. And so we have started the survey with MEQ1, which we call the HSC Niji blue. And that had started in February, where we still have to get the observing nights. So although I said it started, so it depends on the how well we do to get the observing nights. But well, okay. And then now MVQ2 to MVQ4 are now under fabrication. And then once those are delivered, we are gonna do the full color survey. And so this is the current status of the HSC Niji. So where we actually conducted deep observations on the Cosmos and the EDF nodes in February and June, respectively. And so that photo was a first slide of this filter. So I went to NLJ to the observations with my students, and then all of us look so happy. And but we found some issues because we did not have an engineering run before doing these observations. So we found that there's a light leak at the center. So this is due to right. So so actually we found around the center of the field. Well, those are the structure holding the filters, and then at the tips on here. So those are not really properly coated. So we had a like 1 millimeter or 2 millimeter gap. And so we tried to fix this, just putting a small thing. And this was intended for a temporary fix, but we couldn't cover everything. So now we are working on seriously to the fixing this light leakage. So we are going to do some mask, a little bit more larger mask, where actually we did a measurement of the how much coating were missed like a few days ago, and then we are planning to make some mask for this. And actually we already have October round, so that's gonna be 2 nights from Hawaii and 1 night from Gemini. So this collaboration works quite well. Unfortunately, we couldn't get any nights from a Japanese community, but we got the nights from the UH and Gemini. So this is one of the highlights where I will just show this slide related to the science. So well, for cosmology, well, the big motivation is to selecting the Lyman alpha emitters, and then with MBQ1, the Lyman alpha emitter falls between like redshift 2.3 to 3.2, and so right, so we did some tests. So we first selected the Lyman alpha emitter like objects from colors, and then well, we do not have we didn't do the follow-up observations. Instead of that, well, the DZ people already did a follow-up with their sample, Odin and IBIS and SPRIMECAM. So Odin is a narrow band survey with TechCam, and IBIS is an ongoing medium band survey with TechCam. And SCAM means like spring medium survey that was done, I guess, 15 years ago or so. So using those data, so they selected the LA candidates and then did the follow-up. So they have a receipt for those galaxies. So what we did is we matched our LA candidates with those Odin IBIS SCAM sample by array deck. And then for the matched object, so we plotted this redshift. So well, this figure shows the selection goes well. Yeah, yes. Okay, great. So this is a summary. So HSC NIJI has started, and then this is a huge collaboration across the multiple communities. And then there are lots of science cases already proposed across the field. So for example, cosmology is a high-Z cosmology with LAs, and then protocluster search, and for AGN, so people are interested in little red dots and obscured AGN, high-Z redshift, and the galactic archaeology. So people are interested in searching for extremely metapolar galaxies to search for the fast pop-3 stars. And then so we are doing the synergetic studies with DESI Run 2 and Euclid, and possibly we could run a second PFS survey to follow up those LAs. And we already conducted a pilot deep observations with Cosmos and EDF nodes. So, well, the last thing I want to add is that the HSC NIJI can be a good precursor for the Rubin 2036. As I said, we have already corrected the cases for the HSC NIJI. Now we are compiling that as a white paper, but I think that is a good input for the to think about what we can do with Rubin 2036. So that's it. Thank you.
Thank you. Any questions?
How deep will you go? What magnitude limits?
Yes. So I wasn't clear on that. So for white survey, we go to either 25.0 and 25.5. We are still under discussions, but there might be 2 layers even in the white, like a 25.0 and 25.5. Yes. And then for deep, it's like 26.5.
So just to make sure I understand, I was trying to remember the plot you showed before. So the wavelength range is similar to what we have in Rubin, but the difference is that you will go from say 6 to 16 bands. So photo Z should be better. Is that the main point?
So can you repeat the last sentence?
So effectively photo Zs will be better is the main
Yes,
difference
yeah. So I didn't show the plot, but yeah, photo Z will be improved. And actually, so Jeff Newman did some study like to bridge the spectroscopic calculation, and so it's a spectroscopy for the calculation, and also the Rubin broadband that medium band can bridge those two nicely.
Hi, I was just curious which of the medium bands is being used for the galactic archaeology science case?
Yeah, so they are going to use, I think a 465 or something I forgot which lines they are looking into. Like I remember that they are looking for calcium, but I'm not sure that is for this band. But yeah, also they also for galactic archaeology, they plan to do another survey with narrow bands, and which is less than 400 nanometers. So combining those two, they can do a better identification of the extremely metapolar galaxies.
Let's thank Hiro now one more time. We have one more talk online, and then after that we can do some discussion. Suber, are you online? Can you unmute?
I'm here.
Are you able to share the screen?
I was hoping that you guys had it in the deck.
Yeah, we tried your slides, but the file was corrupted.
Okay. Let me grab a copy then. And can I share?
I
And
think so. Can you try? Okay, we see your slides. If you want to put them in presentation mode.
just 1 second. Let me get there.
Yeah.
Okay.
Yeah, go ahead. Thank you.
Just 1 second. I'm going to, well, it's not that, I'm going to work from one slide and I want to really talk through it more than, see, can you still see the slide?
Yes. Yeah.
Okay. I want to talk more about what it is that we would be looking for. Oh, by the way, I'm Super Corley. I'm the team lead for Transiting Planets in the TPS colloquium collaboration. And I just want to talk about exoplanet usage of Rubin 2036. It's really it's about what we don't know that is the core of our thinking. The core of science is to turn observations into understanding. So in the 1990s, Hubble gave us observations that turned cosmology on its head with the new directions in dark energy, accelerating expansion, the deep field, etc. And again, I'm just going to leave that one slide up instead of flicking through. For the last few decades, exoplanet science has been muddling along with most of what we know having been delivered by a few key surveys. However, even the really big ones have their limitations. Kepler, for example, represented on this projection that you see in the slide by the small red rectangle just at the edge of the galactic disk, never really sampled the broader population of the solar in the
Well, we cannot see your slides, but you said you were just gonna talk without moving your slides.
Yes, you're just
we
looking
can
at
only see the first slide.
Yes, that's all you need to see. In the upper left quadrant of that projection, you see a small red rectangle, and maybe the fact that you can't see it is a good indicator of how small Kepler really was. TESS, at the same time, sampled the entire sky.
But we only see the title slide. We don't see the slide with the plot.
Okay, why is that? That's what I've got up.
Okay, thank you all for helping.
So you're seeing the title slide?
We only see the title slide. We see, yes. So is there any other slide you wanted to show?
Yes, I'm trying to show the third one in my deck.
Try starting the slideshow and advancing with your mouse rather than the keyboard, maybe.
Yeah. Yeah. Now we see it. That's better. Perfect. Exoplanet gaps. Go ahead.
Okay.
Thank you.
All right. But I want to refer to my notes if I can. Can you still see that if I'm not showing it on my screen? That
Yes,
way?
the exoplanet gaps, he says. That's the title of the slide.
Okay. And you can see this small red rectangle. You see that now?
No, it got really bad. We cannot see this. We see a giant arrow. So you can leave it like how it was before. Just leave it like that. That is perfect. This is perfect. Don't do anything. This is perfect. Yeah.
Okay.
Thank you.
Okay. Cool.
Yeah, that's fine. That's fine.
Okay. Sorry about that. Okay. As I was about to say, TESS, unlike Kepler, did sample the entire sky, but it limited its observations to really the brightest and the closest stars. So it really was not a broad survey in that sense. So after decades of searching with relatively small instruments, in addition to those two main surveys, there is the new opportunity in the 8-meter telescope with Rubin. So what do we want to do? We propose to focus on the galactic disk. That's about 3,600 square degrees in total that we can cover in 360 of Rubin's pointings, so that we can capture the exoplanet transiting ingress and egress and a comprehensive dip. We propose to do 20 exposures per pointing per night. Since cooler stars and close-in orbits mean short transits, and hotter stars and wide orbits mean longer transits, we have to anticipate an adaptive observing strategy. To begin with, we propose a nightly 5-hour window. I know you guys are going to think we're greedy. We can cover, though, the whole galaxy in about 24 nights. And if we follow this 24-night cycle, it's like the 3-night cycle that Wide Field does, but we're talking about 24 nights. Means that we get repeated, complete coverage of every point in the Milky Way. This repeating process means that we increase our chances of multiple full transits and step up to confirmation, not just identifying candidates. That's important in this case because what's really missing in exoplanets at this point of time is a real population study. Now, continuing with what we are offering or trying to get access to, we know with 5 hours we can get a G9 class star with an exoplanet in a 30-day orbit without any problem and keep that for 5 hours. We can accommodate things brighter than a G9 and others, but later we'll talk about how we have to modify the strategy that we've been talking about. So Hubble didn't just answer questions, it created entirely new fields of astronomical research. In 2036, we have the chance to do something really dramatic with exoplanet research. We need Rubin's observational power to fill in the gaps in our assumptions. It's time to stop imagining what's out there and understand what's really out there. And of course, we know that this proposed survey would be just as interesting to a number of other science cases who need a higher cadence rather than just us. So that was telling you what? Let me tell you a little bit about why. This is sort of my backstory argument. In the case that you aren't aware, and many of you may not be, that papers were written and estimates were made about the power of Rubin in doing exoplanet research. It dates back to the original science book in 2009, where there was a substantial explanation of what was expected. But after 22, when the science was more defined for Rubin and the cadence began to be very defined, we sort of got boxed out by the cadence strategy for doing a lot of exoplanet research. So those early papers that were written that talked about hundreds of thousands or tens of thousands of exoplanets being discovered with Rubin, we have determined subsequently that's just not going to happen. On the other hand, The current decadal survey, which represents one end of the public spectrum, and the recent Pew Research study represents the broader spectrum, but both of these surveys show an interest in exoplanets and planetary science. And in fact, they name exoplanets and planetary science in their priorities, even though they may not be at the top of the list. But there are a lot of other areas and science cases that are not on that list either. But exoplanet research is extremely popular with the community at large. That's the gist of the story. And there is a huge community science population out there that's also, of course, very interested in this. So um, that's the basic gist of what we want to do and why we think that it's important that it be considered. And I guess I can just sort of leave it there for now. We can talk more about it when we get into the groups. By the way, of course, we're talking about the B group, where the focus is on cadence, being what's driving us. Thank you. Any questions?
Thank you. Anybody has a question other than Chris?
I don't want to ask.
Hold on.
Thanks. I was just curious about the magnitude range of the candidates and how PRB follow-up might work for confirmation in this case.
Well, the problem is the confirmation. If we do multiple full transit capture, we can begin to move away. The current process is typically that someone identifies a candidate and somebody else comes along and does a follow-up observation and does a confirmation. If we want to build real population studies for the galaxy of exoplanets, we need to somehow automate that process and remove the second step or build that second step into the pipeline that we're working with currently. We're following whatever Rubin is giving us at from 16 to 25 as our depth. We overlap with Gaia up at the 16 end of that range, all the way down to 21. So we can do a lot of collaborative work, again, automating the process, but talking back and forth between Rubin and Gaia for one to do some of that confirmation work.
Thanks. Maybe this is a similar question. I don't really know much about planetary science. So if you do transit studies, so you manage to identify a population of exoplanets, so you'll have the photometry, I guess, and that will allow you to identify them. Is that all you need to do in order to do population studies? I mean, you know the colors, but will you need other observatories to follow up in order to be able to do science, or can you gain everything that you need to know to learn about exoplanets and their orbits and their nature just with this data sample? Thank you.
We recently published a paper about prospects for exoplanet science in Rubin, and we had worked out a process using simulations. The key was that typically when the photometry is collected, it's phase folded, and you end up with one light curve representing the transit. But if we follow the process that we did with our simulation study and actually capture multiple full transits through a period of time that are repetitive, that confirm the period, we're being led to believe that we can consider that confirmation without the need to go to RV or another telescope doing confirmation work on the same targets. So basically, the pipeline would be front to back multiple full observations of a transit so that we have definite confirmation that this is both an exoplanet signal as well as it is producing a clean, pure periodic frequency. Does that answer your question? I'm going to stop sharing now.
I have a two-part question.
Okay.
One, what would you do with all of the time?
Well, 5 hours only gets us to that G9 stellar type. So we would use the whole 5 hours to do that. The problem is you work your way up the ladder, you have to use a lot more. The transits are obviously taking a lot more time, so you can't even do them in a single night. So we will have to figure out a way to stitch together multiple nights of getting the ingress on one side and the egress on the other, and trying to stitch together what's happening in the middle in order to generate the full transit. But we don't want to sort of overdo and keep everybody else out of the instrument. We can agree that we don't need the full night's observations.
I appreciate your politeness, but I think the spirit, and I just suggest this to everyone, is we are looking for science motivations to do another, say, 10 years or whatever we want to say. So the science should say, this is what we should do. If we have a 2% time science case, that's not as clear a driver. So I really encourage everyone to think very like, what would we do to address the science question in this field with this whole thing? Sure, we'll have to figure out what we actually do, but I'd be interested in that constraint. And the second question was, what if what you had was a set of filters like Kiranal just showed us, and you rotated through and you got the transit in different filters during that time?
That's helpful to us because it helps us to distinguish whether or not there's stellar activity involved, for example. So if you get the same kind of transit signal in several different colors, then that's confirming that it really is an exoplanet signal.
Let's thank Hubert again. Thank you very much. Thank you to all of our speakers. We have about 10 more minutes, and that's not a lot of time. But I was still hoping to have some discussion. The talks have been great, and they have already generated some discussions and food for thought. But maybe in these few more minutes that I have, I wanted to maybe open the floor to see if anybody wants to contribute something. Oh, yeah.
Yeah, thanks very much. I think rather than put a damper on everything that people are thinking, I want to do the opposite, and that is to encourage everyone to be even more creative. These are all great ideas. What I haven't heard today is anything about the cost of doing these things. Right now, this survey is costing the government around just say $1.5 million a week, roughly. In 10 years, we would hope there's a USALT on the horizon and maybe other things. There's NGVLA in our pipeline as well. So all those things are going to cost a lot of money to operate. And so if this observatory were to cost, again, the same amount it's costing now, that's one thing. If it's costing half as much, that's another thing. So I would very much encourage people to think about how you can run this observatory more efficiently with the next survey or the next plans for it as a part of your thinking too, to inspire some more thinking.
So maybe I'll respond to Ed. I think some of us have been thinking a little bit about this, and wondering, recognizing that the operating cost is large. But at the first order, the operations, especially the pipeline operations, which is a very significant part of the cost, are really tuned to the LSST. And as a start, the whole of reanalyzing the images, which is baked in to LSST, is not clear that you would need that in this period. So, that's a first comment. I think for next week, probably that topic is out of scope. But you're absolutely right. Going forward, a real serious look at the costs is definitely necessary.
To make a comment regarding timing. So it is true, Andres, you mentioned this, I believe, that the decadal survey is coming up, 2030. And normally they reach out to the communities at least a few years in advance of that for feedback and for white papers. And so I think that there's a very big chance that we will have a problem with a whole lot of bright satellites. And that the problem will actually start around then. They're going to be launched in just the next few years. So this is an opportunity for us because by that point, we will already have some data on this and we will know how bad it is. And we'll be able to make some mid-course corrections for that.
One thing I haven't heard mentioned too much is about the sensors themselves. It seems the sensor technology with CCDs, which was what was put in this telescope, was 10 to 20 years ago technology. And nowadays they do have these scientific CMOS sensors that are much faster and don't require quite the cooling. So that would save on cost, and it would also perhaps help with these satellites. It seems like that would be a good project to put into place for something from 10 years from now.
What was that? It's CMOS. He's asking about that. Yes. And that's one of the topics actually that we have for the workshop.
So that was one of the suggestions of one of the previous white papers. And that's a new instrument. And you have to get started building it right now. And it's expensive.
Yeah. So that's exactly right. I mean, that's a topic that did get a good look at, in the white papers and the workshops 5 years ago. And definitely, I think the conclusion one draws for Mercat tells or other IR sensitive image sensors, we don't have the optical setup at Rubin to do that. There's no cold stop. There's no re-imaging. That would take a major rebuild of the entire top end, if it's even possible at f1.2. The modern type of CMOS that operate in the optical, there are other issues, right? They're not deep, so they don't have good red response. There's no four-side buttable scientific grade sensor on the market. They're fast. They're certainly low noise devices, but it's not clear that any of the science we'd be interested in goes in that direction to very fast images. But if that's something that emerges, maybe it could be considered. But I think my personal conclusion is the same as Tony's, that the current focal plane is probably the one we should think about.
Yeah, apart from, there's been a lot of discussion of capabilities, but one of the things that I haven't heard spoken about, we have a fast telescope and we can put narrowband images on there. That seems like it would be an ideal thing for, surveying for nebular line emission over broad areas of diffuse emission. Sorry. Let me try that again. We have a fast telescope and we can put narrowband filters on there. It seems like an ideal situation to go after, nebular line emission over diffuse emission over large areas in the galaxy and outside the galaxy. I haven't seen that talked about yet.
Lyman alpha ICL. Lyman alpha emission from the ICL and galaxy clusters.
The science that a lot of people would like to do and we cannot do with LSST. LSST in the time domain, it falls short of like the area, the region of the time domain where there is discovery potential, which is fast transients.
So I think that would be something to come out next week. I think the previous round didn't look, super hard at that direction. Yeah, I think there are other questions because it would change the capabilities otherwise. But yeah, I think that's definitely in scope. I hope that comes up next week. To Jim's point on emission line filters, there is a constraint because of the fast optics. And when this was looked at, and I think Chris Stubbs looked at it most closely, it looked like 20 nanometer bandwidth was about the smallest you could push filters to because of the big angular range of the incoming beam. Maybe that's something people could look at as well. I think we don't have a design for 20 or 25 nanometer filters, bandwidth filters anyway. So that's an area that will certainly need work to pursue the narrow or medium band option. Of course, what we just heard from here now, shows some existence proof in that direction.
So thinking about science drivers, I think one thing that's different compared to when those papers were written for P5 and the decadal survey is now we have some evidence that we might have some weird things like dynamical dark energy, right? So we don't know that that's the case yet, but if we fulfill our role in LSST of really showing that lambda CDM isn't right and something is changing, either it's dynamical dark energy, which is very weird with these phantom crossings, or some other strange sort of thing, then I think we should think about what we would need to do to then nail down exactly what was going on and measure those parameters carefully. It's not obvious without thinking about it what you would change, but I think that should be a real science driver. Thank you.
I was sitting in the back thinking about cosmology as well, Chris. So this might be a question for Hira now, but others in the room as well. So I thought your presentation was inspirational. You're already living the dream with the medium band filters at HSC. So it made me wonder if we just thought about putting a similar filter set on LSST-CAM at Rubin, how close could we get to the Spec S5 science case, which imagined a spectroscopic survey out to higher redshift, looking at more volume and so on? We wouldn't be able to do as well as that, presumably, but we might be able to get some of the way there. And it'd be interesting to see how far we could get with that. Have you looked at that question from the HSC perspective?
Yeah, well, right. For HSC NIJI alone, yes, we looked into the constraint power, but not in context of the Spec S5. So what we can do with our imaging, I mean the LA sample, is cross-correlating the LA and CMB lensing, and then get weak lensing signal. And then also combining with the autocorrelation of the LAs, so we can do 2 × 2 point. So this is what we can do. I haven't looked into what happens for the LSST area yet, but this is something we can look into. On the other hand, Spec S5 can do full shape analysis using the spectroscopic data. So our probes are different, and how ours can be, complementary. So this is a question to ask. But one thing I would like to note is that for Spec S5, they really need, they definitely need targets. So for that purpose, the LSST medium band, for example, should start earlier than Spec S5.
Yeah, just to elaborate on that point, right? So the medium band G band filters for IBIS, which were being shown, are the targeting for DESI Run 2. So it's not, you're not going to replace Spec S5 or DESI with these medium band filters, but you need them in order to do the high redshift targeting. So I don't think, I mean, I don't think medium band filters are going to get you to the spectroscopic science case, but they're needed in order to enable the spectroscopy to come along. If you start talking about very narrow band filters and like getting to, right, like 30 narrow band filter photo Z's, then maybe you can start talking about trying to do more 3D cosmology.
And the narrowband filters, I wonder what we can learn from our SphereX colleagues who have, it's not really narrowband, but there's some sort of, you know, continuous kind of set of filters.
I can say something about that, and I've been sort of wondering whether to do some back of the envelope work on something like this. I don't know. Show of hands, who knows what SphereX is? Okay, let me explain it briefly. So SphereX is a currently in operation NASA Space Telescope that has a focal plane array that covers 750 nanometers to 5 microns on 6 detectors, and each detector has a linear variable filter on it that allows us to get a low resolution spectrum for every point on the sky by stepping the detectors across the sky. So the filter bandpass ranges from R of about 40 to R of 120, depending on the detector, and it varies continuously across the filter in front of each detector. So you get that's the kind of resolution of the spectrum that you get. Just to put this in context, you know, we're going to produce a catalog by 2028 from this project of something like a few hundred million to over a billion redshifts from these low resolution spectra. So one thing that I've been kind of wondering is if one could rebuild the camera to put filters like this directly in front of the detectors. They couldn't be in the current filter location. They'd have to be sort of SDSS style permanently installed and then collect spectra by stepping across the sky. It seems to me this isn't the first thing that you would do at the end of the 10 years. I think there's plenty to do probably with narrowband filters and things like that, but it might be a third generation thing to do because it's working really well. I have thought about it a little bit, and there are some possible gotchas where that might make this not work, including the 20 nanometer bandwidth restriction that was mentioned a few minutes ago. But I think it would be worth considering. I'm very sad I can't come next week because I would love to just like go into a room with a couple of knowledgeable people and brainstorm this. Because it has to be the wavelength has to be like well defined per pixel, right? So it has to be like right on top of the detector. And in fact, with the very fast beam that we have, like that's one of the possible gotchas is that you can't define the wavelength very well because the cone is so wide, unless you can really get the filter all the way down on the detector.
Okay, I think we're a few minutes after the hour, but the discussion has been very interesting, and I do invite people to continue talking in the Slack channel for this in the Slack space of this meeting. I will share the Zoom link and the agenda for next week. And as I mentioned here, these are the questions that we want to ask the participants of the workshop. So of course, I want to hear from you, especially if you haven't had the chance to speak here, because as we can see, there are many ideas and I'm very excited. And thank you very much for coming. Yeah, thank you and enjoy the week.